Yeah, good afternoon and welcome to the Cryosphere Pavilion. My name is Christina and I'm a geophysicist at the University of British Columbia, and I'm an early career scientist volunteering here at the pavilion. And I would like to introduce our next session, which is entitled Climate Overshoot and the Cryosphere. And our first speaker will be Pam Pearson, who is the director of ICCI, and she will kick us off with a few opening remarks. Thank you.
Thank you so much, Christina. It's a real pleasure to welcome the Provide group here to the pavilion today. I'm on the advisory board to Provide. That's been an honor to watch this science evolve over these years. And I honestly don't think it is an exaggeration to say that in many ways, this is the most important side event taking place in the pavilion over these 2 weeks. Why is that? Because overshoot, when it comes to the cryosphere, should not be an option. One of the main, perhaps the main messages we're trying to get out to the policy world through the activities and the side events at the Cryosphere Pavilion, through the State of the Cryosphere reports, is that cryosphere responds primarily to peak temperature. And so overshoot, even in the term, it sounds like, well, you overshoot and then you come back down again. The problem is that for much of the cryosphere, it stays up at that overshoot period. And demonstrating that and showing how glaciers will respond in particular, but also other elements that are part of the Provide studies, is a really important science policy effort that policymakers need to be aware of. Because one of the things that I think those of us who are here today, November 19th, Tuesday of week 2, 2024, COP29, is that the urgency in these corridors seems to be missing. And when policymakers understand the implications of overshoot, hopefully that urgency will come in here. So I won't delay the actual science any longer. It's my great pleasure to introduce Carl, who will give an overview of the Provide project and some of its findings. Thank you.
Yeah, thank you very much, Pam, for your kind words and also for the support and all your fantastic inputs to the project over the last 3 years. It's a Horizon Europe project funded by the European Commission with 70 partners that we've been working on. Actually focusing on the topic of overshoot, but also then on the implications of this, including for providing climate services and all the way to the question of what does it mean for adaptation needs. And yes, our stakeholder advisory board has been instrumental in guiding our work and disseminating our work like we are doing today, and your support throughout the years, as I said before, is really much welcome. Everything we did in the project, and you're going to learn about this a little bit more, you can explore on our dashboard, including a lot of different cryosphere impacts for policy relevant scenarios, down to the level of soon even glaciers on the country level, or even individual glaciers. So we are still working on actually providing a lot of detail on the cryosphere level, and you're going to learn a lot more about this in our side event, as with what it actually means in terms of the impacts of any such glacier change. By my colleague Fahad, who will present a case study in the upper Indus Basin, basically from glacier runoff. Ultimately, the project is really kind of an interconnected pipeline of trying to look at a wide range of different scenarios, much more oriented towards policy and recent developments than what the RCP scenarios would provide, and then go all the way to sectoral impact projections and into the implications for adaptation, and providing all of this output really in an accessible format, including on an online platform that allows you to individually explore these implications. So what are we doing? We're actually looking into the scenarios, or primarily into the scenarios identified by the screen. So this provides us with a good spectrum of where we're going in terms of current policy, but also in terms of what are transformational pathways that would keep the 1.5 limit within reach. And what does this mean? And what does it mean for avoidable, unavoidable, and potentially irreversible impacts? And Pam has already raised that point with the question of irreversible impacts, in particular in the context of the cryosphere, is of course of particular importance. We use those scenarios, we project it into sectoral impacts, and it allows us really to actually produce graphs like the one that you see at the bottom right, in terms of questions of avoidable and unavoidable risks through mitigation. A lot of the climate risks that we foresee unfolding over the 21st century, unfortunately, are to some extent looked in. Even the world at 1.5 degree of warming is going to be worse than the world we see today. And many impacts of climate change in the cryosphere, in particular, are time-like, so they're going to unfold over time. Yet what you do see over time, like the light gray bars, show you that a lot more can be avoided as time progresses in particular, and that mitigation pays off big time, in particular for some of the tail risk impacts and cryosphere changes that we're seeing. And you're going to see a lot more on this, specifically around questions of cryosphere changes and glaciers going forward. Just to mention that we basically go all the way for a variety of sectors, including with high resolution information on the urban scale, 440 cities worldwide, but you can also explore a bit more a heat extreme focus and urban adaptation focus, but this is all basically under one roof of this particular project. So I have a few messages for you that I want to bring across. And I start with the message and then I try to justify it. The first one is overshoot comes with irreversible risks. Pen has been speaking to that, so let's put some actually meat to the bones of this particular construct. So first, starting with basically the legacy of overshoot for the cryosphere and changes over time. This is global sea level, as well as the additional temperature response from greenhouse gas emissions from peatland and permafrost under overshoot. We quantified this over a range of scenarios. What we find is a remarkable linear relationship that we didn't put in, that is actually a finding, between the length of the overshoot and the actual outcome. So 100 years of overshoot would commit about 40 centimeters of sea level rise in 2300. That's an irreversible commitment. If you feel it doesn't sound so much, then actually you want to consider a risk framework that actually looks at the upper limits of those if particularly some of the irreversible processes triggered at ice sheets would unfold faster than our central estimates. This could actually go up to 1.2 meters per 100 years of overshoot. That's a very significant number. And you can see basically the risk of overshoot and the irreversible commitment they're going to reshape the global coastlines over centuries to come, and it is something that we need to consider very, very carefully. Secondly, we can actually wonder what happens to some of the risks of irreversible thresholds. I mentioned it a little bit already, including particular cryosphere thresholds, such as the Western Arctic ice sheet and the Greenland ice sheet. And we did it in a study that we just published in summer, looking at the risks of those under overshoot pathways. And we can clearly see what Pam has highlighted also in her opening remarks, that peak warming matters for the risks of crossing irreversible thresholds. So what you see there, the graph is the peak temperature at the bottom, and you do see and the tipping risk on the y-axis, and actually on the current policy pathways that will bring us to around 2.5 degrees by the end of the century. We run a more than 50% risk of actually seeing a triggering of a tipping point over the next 300 years. And if you were to limit peak warming to much lower levels, close to 1.5, this risk is greatly reduced. So this all really matters, and obviously speaks to the irreversible questions around overshoots. I should mention a few caveats on these studies, because the timescales on how fast this tipping may emerge are not very well constrained, and unfortunately in the past we've seen these systems are potentially able to respond a lot faster than we hoped they would. So maybe our results are even conservative in that sense. Nevertheless, I wanted to also speak to the question of, well, yeah, then why even talk about overshoot, or what to do actually then if you were in an overshoot world? Because it doesn't, if you were exceed the 1.5 degree limits, it is still the question, why would you go down? Or what are the benefits of going down, and how do you actually tackle that question? So the second big message that I have, irrespectively of what the warming level is we end up, which should be as low as possible, a long-term warming reversal can limit the risks, in particular for the cryosphere. So if we were to reverse warming, impacts will be lower than when we stabilize. Regional climate impacts can also basically probably still be avoided, and we're going to reduce long-term impacts. So this is a similar graph for global sea level and permafrost and peatland loss, but now comparing a long-term decline trajectory aligned with net zero greenhouse gas emissions compared to temperature stabilization. What you do see is, again, that you would have about 0.5 meter of avoided sea level rise by reducing long-term temperatures, again, compared to just staying at whatever level you are. And in the 95th quantile, this number could go up to 1.5 or 2 meters. So potentially, to limit cryosphere risks, ultimately you want to limit warming as low as possible, and then you still want to go down in the long term to limit the commitments and legacy that you're going to see play out in the cryosphere for centuries to come. Similar things apply to tipping risks. I showed the peak warming dependency earlier. And now I show the dependency on achieving net zero greenhouse gases and therefore declining temperatures in the long run. And what you do see there very clearly that pathways to the right that don't achieve net zero greenhouse gases and don't bring temperatures down in the long run, ultimately we'll see tipping points potentially being transgressed and irreversible dynamics being triggered. Whereas if you were able to limit peak warming and then go down in the long run, we may still be lucky. I mean, we need to say this is all not in our hands anymore in full, but I think it just shows that the potential for risk reduction, at least in our current understanding, is still very substantial. And we need to account for that. And with that, I want to hand over to my colleague Fabian, who's online. Fabian has been leading our work on glaciers, and we're now going to do a zoom in. I've been given a bit of a broad overview of what the project is about and global cryosphere implications, and now we're going to look into the glaciers. And there's a lot happening there, so stay tuned. Over to you, Fabian, and I hope you can hear him well. I appreciate the acoustics in this place are a bit of a challenge. Thank you.
Thank you, Carl, and I could hear you very well. Thanks. I'm going to share my screen first. Okay, I'll assume you can hear me and see my screen now. Thanks for having me, and sorry I can't be with you today. I would like also to use this opportunity to really thank the Pavilion and everyone for doing 2 years, and I know it's extremely intense. So thanks for all your work. So I'm going to
Fabian, if you can hear me, we can't hear you yet. I don't know if you muted yourself.
No, I'm not muted. I'm not muted, so I should be there.
Okay. Yes, okay. It works now. It was on our end. Okay, thank you.
All right, then I'll go back to my screen. I was saying my thanks to the ICCI and the Cryosphere Pavilion for organizing this. I've been there for a couple of years, and I know how intense it can be. And thanks for all your hard work. And thanks also, Carl, for the introduction. So my name is Fabien Motion from the University of Bristol. And in this project, I've been dealing with mountain glacier changes. And these are all the ice bodies outside of the two big ice sheets, so in the mountain regions of the world, but also in the periphery of the ice sheets. And I'm going to talk about how you can use the Provide dashboard. I'm going to make a short introduction to explore glacier change in various overshoot scenarios. Glaciers are melting worldwide at an accelerating pace, and they still contribute to about 1/5 of the observed sea level rise and leading to coastal floods, such as in this picture. The other component being the ice sheets and thermal expansions of the ocean. And so glaciers are already losing mass because of past warming, and as they do so, they also make changes in downstream regions. So in regions, for example, which rely on the water from the mountains and from glaciers for their agriculture and their water supply. When glaciers are disappearing, this source of water, especially during the dry months, is vanishing. And people and communities have to adapt, and ecosystems have to adapt to these changes. And as glaciers retreat, they also can lead to various geohazards. Here, this is an example from Sikkim in India in 2023. This is what we call a glacier lake outburst flood, which is triggered by glacier lakes such as the one on the picture to the left. And so we do definitely care about glacier change. And then what we do is using numerical models of glacier change to simulate their future. So here, this is an example for a famous glacier in the Alps, and scientists such as me and others in the room are using the numerical models of glacier change to simulate their future. And these results are then included in the Provide dashboard, aggregated results, not at the single glacier scale like this one, but aggregated at various country levels and sectoral levels. And so here, this is I gave you a QR code if you want to use it, or you can use the link below. I'm going to introduce how these data then are feeding the climate risk dashboard, which, as Carl said, contains many other indicators such as heat stress and other elements. But I'm going to focus on glaciers here. And so for the rest of the presentation, I'm going to use these 3 scenarios out of 10 that we have in the dashboard, which are providing a wide range of outcomes consistent with current policies. So the warming of about 3 degrees, which would be like unabated emissions, such as current policies are predicting, or stabilization at 1.7. So this would be delayed climate action, or an ambitious shifting pathway scenario where we are actually at 1.3 degree of warming at the end of the century, which would be the best outcome. And so if you remember these colors then, and we have a look at glacier volume in Austria, this is a graph from the dashboard itself that you can generate yourself on the dashboard. You see that in Austria, as a country in Western Europe, you see that there is not much difference between scenarios until the very end of the century. And you can see also, if you look at glacier volume, that we are going to lose, no matter what, at least 80% of glacier volume in this country. And this is because warming has already occurred and glaciers are already too big for the level of warming. And so this is a mass loss we call committed, which implies that we are going to lose most of the glaciers in the Alps anyways. But you still see differences between the scenarios, with the current policy scenario leading to a complete deglaciation, while the shifting pathway scenario allowing for, with uncertainty, of 20% of ice remaining at the end of the century. So our actions, even in this country where glaciers are mostly going to disappear, our actions matter. And the provide dashboard then allows to explore risks in a more probabilistic manner. So here, for example, you can choose an impact level. Let's say we want to know the risk of losing 90% of our glaciers in Austria. Well, the risk by the end of the century is 100% in a 220 climate policy. This is what this graph is telling us. So we are going to lose 90% if we continue under current policy. However, with a more ambitious shifting pathway, this risk lowers down to 50%. Perhaps another way to read this plot is to change the impact level and ask, okay, what's the risk of losing 50% of our glaciers in Austria? And here you see by the end of the century, this risk is 100%, basically. We are going to lose 50% of glaciers volume in Austria, no matter what happens. But in Austria, maybe glaciers are not that relevant for water resources. They're relevant for tourism, and also they have a symbolic value. But in countries where, like Peru, where glaciers do provide water resources in the dry season, here you can see a much wider range of outcomes depending on our policies. Glaciers have melted already quite substantially in this country, but the remaining ice can be saved by a large extent with an ambitious climate policy, while current emissions would lead us to 20% of ice remaining at the end of the century. Again, a way to look at it is to use this impact level of 50%. So let's say we want to preserve 50% of glaciers in Peru. Well, the risk is much lower if in a shifting pathway scenario than in the current policies. And so I really encourage you to basically use this dashboard to explore impacts such as on mountain glaciers, but also heat waves and other sectors to explore this impact that our policies have on various climate impacts. With the last minute I have, I'd like to talk also about risks beyond 2100. And so I'm going to play another of these videos here. This is showing glaciers in the Karakoram in Pakistan. And I'm going to stop the video by 2100. And on the left, you have a very low emission scenario. And on the right, you have a high emission scenario. And you see that by the end of this... Sorry, can you... Yeah.
Where's the Karakoram? Is that the Himalayas?
The Karakoram, yeah, sorry, it's in Pakistan here. It's here. The Karakoram is in Pakistan mostly. And we can see that by 2100, glaciers are still glaciers remaining in the Karakoram in both scenarios. But if we continue then much further in time in a high emission scenario, we are going to lose all ice by 2150 or 2200. So this is because glaciers take time to melt. And here, perhaps even more than with graphs, we can really see the difference by 2300, where most of us won't be there, but we'll still be human to actually see these landscapes. There is a huge difference between a low emission scenario and a high emission scenario where all glaciers are gone. It's a completely different landscape. Okay, I'm sorry if I'm just. There is one last message I want to bring you as well, is that this single glaciers is one example, but if we look at the global scale and we have a look at two different worlds, and here we're looking at worlds where we stabilize at 1.5 degree, a world where we stabilize at 3 degree, which would be really catastrophic, and a world where somehow humanity finds a way then to go back to 1.5 degree after peaking at 3 degrees. So this is a very strong overshoot world. And we must ask ourselves, is the red and the blue world, so 1 to 1.5 degree after overshoot, are these two worlds the same? And I think we can say intuitively that it's not going to be the case. And for the first time now, we have a study in this project which clearly shows that no, a world after an overshoot is not going to be the same for mountain glaciers. And if we look at glacier volume, then after overshoot, so in the centuries after 2300, we can see that there is a clear differences between these two lines. They have the same global temperature, but a world where we have peaked at 3 degrees and then come back to 1.5 degrees has lost much more of its glacier mass than a world where we stabilize at 1.5, which should be the objective here at COP. And I'm not even mentioning what would happen in a 3-degree stabilization scenario, because then you see we are committed to have an ice loss well beyond 2,500 and losing most of our glaciers in the world. And so with this, I'd like to end my presentation and thank you for your attention. And I'm perhaps just going to read the last sentence, which is the most important one. Glacier change is irreversible for centuries after overshoot. And the legacy of today's emission is a long-term commitment to glacier loss with profound implications to sea level rise, water resources, and ecosystems. Thank you very much.
Hello. Hello, everybody. So my name is Fahad, and we are the regional partners in Provide project. So we have a dual role in the project. So we were also looking at Cryosphere, the melting of glaciers, because somebody has asked about where is Karakoram. So Karakoram is the northern area of Pakistan. And I'm also going to talk more about the importance of Karakoram for Pakistan, economy and the resources. So, but for that we need the slides. Okay, so in the time we get the slide on the screen, I would like to say that Pakistan is always among the top most countries at risk according to the German Watch Index, and there is a reason to it. And before going into our the results, I would like to show why Pakistan is one of the countries which is most at risk because of climate change. If you look at the top left map, so it shows the topography of the country. So the north-south distance is almost 1,800 kilometers, and within that distance we have the coast as well as the highest region in the world, which goes as high as 8,000 meters above the sea level. So within 1,800 kilometers, we have all this diversity in terms of topography, which leads to different kind of climate regions in Pakistan. So we have plains, by the plains here, the plain we have added to semi-arid regions. So most of the Pakistan is added to semi-arid, which receives very little precipitation. At the same time, we have one belt of humid regions, which receives monsoon precipitation, so which makes it humid. And the northern region of Pakistan is also has parts of it is also semi-arid, but they have a lot of deposits of glaciers, and it receives snow during the winter season as well.
So because of this diversity, Pakistan has a lot of climate impact. So ranging from, if you consider heat and humidity, so Pakistan is the hottest place on the earth. And Pakistan receives monsoon. Because of that, Pakistan is prone to flooding. Pakistan also has glacier at the north, as I said, and because of that, we have glacier lake outburst floods event, which also contributes to floods. So we have like multiple kind of events. So these are just to name a few. And to make things more complicated, if you look at Pakistan, because the southern part is more arid to semi-arid, the density, the population density is only following the Indus River. So this is the Indus River and its tributaries, and you see all the population, the 240 million people, they are residing on this strip from north to south along the banks of the river. Talking about the density, this is Karachi at the coast, having a population of 22 million people in one city. We have a multiple city having more than 10 million people. So that is the kind of a demographic problem and geographic and demographic problem the country has. Country receives there are two main systems: monsoon during the summer season and western disturbances during the winter season. But Pakistan comes at the termination point of South Asian summer monsoon. So monsoon, after crossing through whole of South Asia, terminus of Pakistan. Any changes in the because of the climate change is going to affect affects Pakistan because it is at the tail end of the monsoon. Similarly, western disturbances which originate from Mediterranean also terminate over Pakistan. Very crucial source of moisture of the northern part of Pakistan. So it also like adds the problem of this uncertainty and changes because of climate change. No, now quickly I will come to the upper Indus Basin. So that's where the Karakoram is. So the north part of the Indus Basin, it has Karakoram region as southern part is Himalaya. So the significance of this basin is that that irrigation plays a very important role in the economy of Pakistan. It accounts for almost 22% of total GDP of the country, and it employs 44% of the labor force. It makes irrigation a very critical sector. But the problem is that because of in this basin, it provides like 40% of the total water resources in Pakistan. This upper Indus basin. So we applied a watershed model, University of British Columbia's watershed model over this region. So these are the details about the meteorological data we use, hydrological data from the Water Power Development Authority of Pakistan. And we use, like, it's a classical study. We haven't considered Overshoot here, but it's a kind of a classic study. Where we have used the GCMs from the AR6, IPCC AR6, multiple GCMs, and we considered three emission scenarios: 1 to 6, which is like below 2 degrees centigrade scenario, and then we have 2, 4, 5, which is the current policy scenario, and a very high emission scenario. So here we have displayed the validation of the model from 1995 to 2007, and you can see that the model is predicting the stream flow quite ably if you consider the model and the simulations. And now what we have done here, that the model we have used is a semi-distributed model, and we have integrated it with the OGGM, which is Open Glacier Global Glacier Model. And then the simulations of this pretty much shows that at different decades, starting from 2000, 2030 up to 2099, that the performance of the model in predicting the glacier value. And that is for the other scenario 245. And here's the important reason which we have seen for this scenario, that the main the flow, it comes during the summer season, and which is very important for the summer crops in Pakistan. But because of climate change, we can see that the flows are shifting towards the earlier months. So that is the time where whether the country needs the water the most. But because of climate change, we can see the shifting of those flows towards the earlier month. So it's going to be a big shift on the sector, which is very crucial for the economy of the country. So in the 1 to 6 scenario, we have like the difference is quite less. It is like around 0% or 10%. But as we go through the high emission scenario, we can see that this shifting is intense, and also the availability of the water would also be low for the very high emission scenario towards the end of the cycle. And this is the glacier area change, and there are no surprises that the glacier areas are also like changing from near term to the towards the end of the century, less in the low emission scenario and high in the high emission scenario as well. For the very high emission scenario, it is alarming rate, almost 80% reduction in the glacier area changing a bit. And that is the difference in summer heat flow. In the low emission scenario, we have by the end of the century, in the last decade of 21st century, we have a reduction of the summer reduction in the heat flow about 30%. But in the current policy scenario, it is going as high as 30% the reduction in the stream flow or the availability of water, which accounts for 40 to 45% of total country resources. And for a very extreme scenario, it goes as high as 50%. 50% reduction of stream flow by the end of the century in the very high emission scenario. So yeah. So that is pretty much it. So these are the findings of our study that I'll just leave you with. Thank you very much.
Yeah, thank you so much to our speakers. And now we can take any questions if there are any from the audience, please. Are there any questions from the audience?
Turn around.
Yes.
Yeah, thanks for a really interesting presentation. So I actually had a question to Carl. You showed us this sort of overview of some of the findings, and you had this very interesting, basically linear relationship between long-term impact of overshoot and the length of the overshoot. Can you comment a little bit on do you have a sense of how long do you predict this linear effect to be ongoing? Do you have a sense of can your models predict when for instance, permafrost or peatland feedback would cease after overshoot, or if the sea level rise would cease at some point, or what's the time scale of that?
Yeah, I think it's a very, very good question. I mean, we were actually more expecting, what we would expect is more something that scales with the intensity of the overshoot, so like the temperature over time. But funnily enough, that's not what we found over the time scale of 2300. So, and that might be due to actually competing effects, because the peak of the overshoot and the length of the overshoot are not independent. If you somewhat constrain the amount of carbon dioxide removal, and therefore the temperature decline rate, the higher you go, the longer the thing is. So ultimately, on the scenarios we look at are all, let's say, reasonably well behaved. They don't go beyond the greenhouse gases, but they don't show extreme temperature decline scenarios, under which I would expect this relationship also to not be as robust as it is in our set of scenarios. Here, of course, you need to consider, even if you went towards a set of set of CDR report as outlined, might be an upper limit for CDR deployment, at least around the century of 7 to 9 gigatons, will not be able, in our best estimate, to bring temperatures down more than about 25 degrees in 50 years. So to actually reverse an overshoot of for example, half a degree, it's going to take you 100 years. So it's a long time. So any commitment, that's something you need to appreciate. And also, the way down is probably going to be a lot harder and a lot longer than the way up, and also a lot more consequential in terms of the effects. Ultimately, we haven't looked beyond 2,300. I mean, we've done, so Fabian has done so for some of the glaciers, as he's shown, up to 2,500. For sea level rise, I would expect some components of the sea level rise to equilibrate until the middle of the millennia, but not the ice sheet. Ultimately, it depends then basically also how strongly you bring temperatures back down again, because ultimately you would hope that you'd be able to kind of meet these systems halfway, where you're basically bringing temperatures down so much that you reach the long-term commitment. But I mean, ultimately, if you were to stabilize warming at 1.5 degrees, the long-term sea level rise commitment over 2,000 years is about 2 meters, right? And then for permafrost and peatland blocks, you will see also some basically like it's slowing down, but at 2,300, the dynamics have not stopped yet. That's the same as we see, and these are very similar with the I mean, this, I think to me, it just kind of shows the legacy of the Cryosphere legacy of our actions or inactions today. Because even in scenarios that peak between 1.5 and 2 degrees, so basically mid-century, 250 years down the road, and we don't even know what a power plant looks like, the consequences of now basically delaying peaking are going to be still very, very visible in the Cryosphere system. So I think that's kind of the message that we are trying to convey.
Is your research being incorporated into the IPCC and their recommendations? I mean, I see that ICCI is created to address this dangerous gap, but how is your data and your research being incorporated into what the IPCC?
Yeah, oh, sorry, I should have told. Fabio, repeat the question for you. Maybe also happy for you to come in. Maybe we can put you on the screen also. The question was how our research can inform the IPCC.
Yes.
I mean, yeah. Ultimately, maybe you wanna kick us off, Fabio, on that, and yeah, please also comment.
Yes, thanks. So the research on glaciers has always been informing the IPCC reports, and so if I think about, for example, also the initiatives we're having like model intercomparison initiatives where all the glacier modelers are combining the results together, and these are usually informing the IPCC report. It has been done in the past, and I'm quite sure the study I've shown, for example, is also going to inform these reports. Where I'm maybe less qualified to comment is how these results then are actually achieving what they should, which is to inform policy. And here people in the room are more able to comment on this.
Yeah, that second part is part of the question too.
Yeah, so IPCC doesn't do its own research. It synthesizes the research which is in the peer-reviewed literature. So in this project, we have published a lot of papers, which will be taken up by the hopefully in the next round of the IPCC report, which is like kicked off recently. We have the 7th assessment cycle, and a lot of almost for all the 3 working groups. The work we have done is relevant for all the 3 working groups, so 1, 2, and 3. So I'm quite sure that this project will inform that question of overshoot and impacts and what should be done in order to avoid the higher overshoot. So IPCC, I think that will be reflected in the upcoming IPCC reports.
I mean, your boards here indicate that there's a dangerous gap between the policymakers' perceptions of the cryosphere and the action and the policy that's coming from it. So I'm a local elected official in Texas. We're experiencing growing loss of water availability, and this is just going to exacerbate it in an enormous way. And I can tell you in Texas, there is just no sense that this is a long-term issue. They think it's just temporary drought, and the next hurricane will fill up the reservoirs and the aquifers, and there's no significant action to try and address it. So there's no sense of urgency around it. And I've come multiple years, and every time I come to this pavilion, I'm more and more alarmed, but I don't see, I guess I don't see it being implemented.
Yeah, I guess I very much agree with you, and I guess if we had a solution to this question, then we all would be in a much better place. So I think we all need to kind of continue to strive together to find answers, and I think we all can contribute maybe bits and pieces. I mean, the IPCC process is probably, let's say, a little bit like the super tanker of climate science, comes around also, on its own timescales. I wouldn't necessarily say reflecting the sense of urgency that we need to act now, but more kind of bringing new science in 5 years down the road. Nevertheless, very important. And just to add to that question, I think ultimately we've been one of the first projects trying to look into this question of overshoot, which is sometimes perceived, not from the scientific side, but I think if it's displayed as another way to achieve the same outcome. And I think what we are showing is that's not the case. Like it's not another way. Like the world's going to be different. There are going to be irreversible consequences, and it's not, it's not a free lunch to do that. It is very consequential. In particular, also then for our cryospheric legacy, for example, as we've shown. Ultimately, this has been identified as something that science should explore more, and I think since we've been kind of pioneering in that space, I hope it can guide like the community's reflection on where to focus our research efforts and assessment efforts also for the next assessment cycle. So I hope basically from the studies that we've done and perhaps been entirely speaking to, this can be helpful. But then there's this other avenue of outlet that would be very interesting to kind of like also then for you to go explore it and provide us feedback, is that we try to at least kind of bring our results like in an accessible format online. So everything we've been showing today, you can explore yourself. You can go and you can ask yourself, okay, well, what's for this climate indicator, let's take heat risks for Texas. What's the avoidable and unavoidable risk over the 21st century? How is it going to go? What can we still do about it in terms of mitigation? What is the basically bottom line of risk that we need to expect, even if we did the best we can? And try to inform yourself about this. We also do this then really on the city level. So you can, in urban environments at 100-meter resolution, explore future heat wave risks, which we hope is very concrete for people to take on board, as are the studies that we did in the regions like Fahad has presented, which are also providing, I think, much more tangible climate risks for people on the ground. And then ultimately, the thing that we then try to do is, and that's then, where all the work is really, is then to try to actually engage with communities and go there and talk to people on the ground to be like, look, what does this mean for you? What does it mean for your planning? What does it mean for your urban planning? What are the, potential scenarios that you could explore, which we've done in 4 case study regions, Islamabad being one, the Bahamas being another one, and 2 European urban environments. And I mean, this was like a big part of the project and a part that I'm particularly proud of all the work that's gone into this and also all the engagement that we had. But we need probably a lot more of that, and at least we try to kind of provide some of the, the climate information that may be the starting point of a conversation, and then explore some conversations. But I very much agree a lot more of those are required.
Are you available to come to various regions in the country? I mean, is this something?
In principle, I mean, that points to the question of like how this funding structure works. So unfortunately, we have a project that's coming to an end, so there's not much more from that. But the provide climate risk dashboard, like and can also very happy to point you to that. I mean, we continue to maintain that one, and we are always keen to explore, what to do with it going forward. So very happy to keep the conversation going.
Just one more point, that we have also tailored our analysis, our research, after getting the input from the policymakers. So we have engaged with the policymakers at the beginning of the project, and some of our work, our analysis was also was in line with the priorities of the government. So the kind of the stances they have taken in their policy documents, such as a national adaptation plan or other city plans. So that is also we looked at the things from their perspective.
Thank you.